we know how to compute products. So we can also compute integer powers of complex numbers like z squared, z cubed, etc. Computing numbers like z to the power 42 or even higher powers is quite a lot of work in this way, of course. Fortunately, we have a nice formula for those higher powers. It's called the Moivre's formula, and it uses the polar form of a complex number. In this video, you will learn the formula and its derivation, and we will use it straight away in an example to compute a high power of z. So, what is this formula? Well, first of all, if we have two numbers, z1 and z2, we can write them both in polar form, like this. First one has modulus r1 and argument theta1, second one with modulus r2 and argument theta2. And of course we can multiply them, z1 times z2, in this polar form. Well, why would we do that? It's quite cumbersome, right? Yeah, that's true, but let's do it anyway. So what happens? z1 times z2. Here we have our z1 and here we have our z2. And we multiply, so we get the r1 times r2, we take that in front, and then we work out the brackets, the cosine 1 times theta 1 times cosine theta 2, plus that's over here, plus I times cosine theta 1 times sine theta 2, which is over here, plus an I times sine theta 1 cosine theta 2, which is over here, and then finally an I squared times sine theta 1 times sine theta 2, which is a minus sine theta 1 times sine theta 2. And this looks horrible. However, we see something nice happening, because this cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 is just the cosine of the double angle of the angle theta 1 plus theta 2. And this cos theta 1 sine theta 2 plus sine theta 1 cosine theta 2 is just the sine of theta 1 plus theta 2. So what has happened? The product z1 times z2 equals r1 times r2, has as new modulus r1 times r2, and has as new argument the sum of the arguments, because it's of the form r1 times r2 times, between brackets, the cosine of theta 1 times plus theta 2 plus I times the sine of theta 1 plus theta 2. So if you compute the product of the complex numbers, and if you have them already in polar form, what do you need to do? You need to multiply the norms, and you will have to add the arguments. So that's the easy way to compute a product. And of course, if you want to compute a quotient of two complex numbers, you have to do the inverse operations. So you have to divide r1 by r2, and you have to subtract the angles theta 1 and theta 2. So let's do an example. We have an z1 with modulus 2 and argument pi over 2, and a z2 with modulus 3 and argument 3 pi over 4. So what happens if you compute the product? Well, the norm of the product will be the product of norms, 2 times 3 equals 6, and the argument of the product will be the sum of the arguments, so that will be pi over 2 plus 3 pi over 4 equals 5 pi over 4. So if you have a complex number already in a polar form, you can compute the products easily. Let's look at consequence. Let's look at one complex number, and let's compute z squared, z cubed, etc. So our complex number z has as modulus r and as argument theta. What happens if we compute z squared? Well, z squared equals z times z, so we multiply our complex number with modulus r and argument theta by another complex number also with modulus r and argument theta, which means for our product we have to multiply the norms, so we get r squared, and we have to add the arguments, so we get theta plus theta equals 2 theta. So z squared, we have the polar form over here, r squared times cosine 2 theta plus I times sine 2 theta. What happens now if we compute r cubed? Well, r cubed equals r times z cubed equals z times z squared. The polar form of z squared has modulus r squared and argument 2 theta. We multiply that with the complex number with modulus r and argument theta. So our new modulus will be r cubed and our new argument will be 2 theta plus theta equals 3 theta. So there we are. And we can go on and on and on with this argument for any natural number. We can compute z to the power n, and you see what happens. You have to r to the power n, and you have as argument n times theta, and that is the Moivre's formula. Z to the power n equals r to the power n times cosine n theta plus I times n. I times the sine of n theta. And this formula holds for any n, so we can use very high n's in this formula. So with this formula we can easily compute high powers of complex numbers. So for example, we have a z equals minus 1 minus I, and we want to compute z to the power 42. Of course, we can just compute z squared, z cubed, etc. It takes a lot of time. Fortunately, we have the Moivre's formula, so we can do it much faster. First of all, we will need the modulus and the argument of this z. Well, we know how to do that. The modulus of this z equals the square root of 2, and the argument equals minus 3 pi over 4. And then computing z to the power 42 is easy because the modulus is just the modulus of z to the power 42 equals the square root of 2 to the power 42 equals 2 to the power 21. And then the argument of z to the power 42 equals 42 times the argument of z. So 42 times minus 3 pi over 4 simplifies to minus 3 pi over 2, and the principal value of the argument is between minus pi and pi, so the principal argument of z will be pi over 2, and we can compute z to the power over 42 as 2 to the power 21 times cosine pi over 2 plus I times sine pi over 2 equals just I. So there we have our z to the power 42. So now we see how we can use the Moivre's formula to compute high powers of complex numbers.